couple quick announcements. So catching up, almost there with the notes. The last two notes that were incomplete before, they're done. I realized though that when I uploaded the probability notes, there's a formatting error where it treats the bars and probabilities as tables in Markdown. So it looks, there's some weird things that looks there. So let me fix that this evening. It should be fixed by this evening. And then the rest should be up. Certainly everything you need will be up by, I think everything you have is already up for the homework by Wednesday. But it should be set, and hopefully catch up by the next, fully for this lecture even today, by the next Wednesday. The project proposals are due today, so due tonight at midnight. Several people have already submitted them, so that's great. We've had a few questions about can you change? Yes, you can, but I really would encourage you not to, unless you really need to. So I mean, you can of course change in response to some feedback I give, but we're having a lot of people with the tutorials emailing me today and tomorrow and yesterday, saying, can you change the proposal for the tutorial already? And that's pretty late at this point. So trying to leave it for the tutorial. That I'm saying okay for another currently, but it will be hard to do your entire tutorial in a few days, and that's due this Friday, remember. So for the final project, try to settle down on topic with your group substantially earlier. And if we do give feedback, start thinking about that, because unlike the tutorial at least, there's a substantial amount of data analysis you have to do on the project to really make a good project. So, okay. So this lecture, we're going to talk about hypothesis testing and experimental design. We're actually, before I start, are there any sort of logistics questions? The next homework's going to be out on Wednesday, and it'll be 2 weeks from Wednesday. Yeah. Yeah, so the TAs are going to, right, it's a good question. The TAs will post the tutorial submission tonight, I believe. I'm asking them to do it tonight. If it's harder than that, it might be tomorrow, if it's a big hard. It'll be an auto lab link that you submit to. So the idea is that we will then post it as a notebook reader. It should render like that, but we will post it ourselves. So you will submit a package to Autolab. That also means in some cases people have in the past had ones that are too big to submit. So I think Autolab has a limit of 10 megabytes or something like that. So if your tutorial is bigger than that, try, and actually you should be doing this anyway, try to host any images you link to, not ones that are generated in line, but images you link to. Make sure those are linked externally. That way you can actually view them in the viewer. They won't throw an error with that. We'll try to make it so you can actually view them if they're just local links as well. But to decrease the size, you can do things like post data on Dropbox and things like this, and include links to it instead of including it all in the submission file. So that'll be out today. That's the submission form. The next homework will be out Wednesday. I do actually have to say that the lecture, I'm going to rearrange lectures a little bit for the sake of the next homework. But the 688 problem on the next homework will cover recommender systems. We'll talk about that on Monday, so not by Wednesday, but the next Monday. The rest you have all the background for, but the 688 problem only, that will get to wait till next Monday to get the lecture for that. Okay, so let's jump into the topic of this lecture, which is hypothesis testing and experimental design. Start with some motivation, then give a bit of background on sample statistics. So again, we're kind of blowing through statistics very quickly here. We did all of sort of point estimation in the last lecture, and now all of hypothesis testing in this lecture. Of course, it's a really, really brief treatment, but I want to give some of the main ideas here. And the reality is, a lot of what you would actually do here in practice, you'll need to then go and figure out how to do by looking up the right tests to run and that kind of stuff from a textbook. I'll talk about basic hypothesis testing, and finally some experimental design. So let's sort of begin with some motivation for this. I saw this comic, I think it was posted on some faculty door when I was an undergrad, and it really stuck with me, and I keep coming back to it. And I actually really believe in this statement here. And so I'll preface this all by saying that for a data science course, I would say we've done almost so far no science so far for a data science course, right? And in fact, the term data science, I think, is a little bit of a misnomer because while it is about analyzing data and sort of making, understanding phenomena in the real world, the huge tie-in with kind of engineering and building systems and data science, at least as it's applied in practice, maybe not as the stats department here, now the stats and data science department would advocate for, at least as data science is applied in practice, there's oftentimes not quite enough science to it. And so I'll try to define what I mean by that in this lecture. But basically, this little comic here is about how mad scientists are really mad engineers because they don't do things like run controlled experiments and making observations and stuff like this. Do they have control groups, stuff like that? Probably not. And so when I say science here, what I really mean by science is sort of determining the truth in the world, in the physical world, determining the truth. And a lot of what we do in machine learning and computer science as a whole is really about system building, right? We build a system that can kind of make cool predictions that sort of that do good things, that seem reasonable, but they're not really quantifying some real effect that's out in the world. And that's going to be the topic of this lecture, at least trying to get at it, is the topic of this lecture. Now, as you might imagine, that's pretty hard to do, right? Going from, this classifier attains this accuracy in this data set to I really think this effect, this input here, this input here really causes this effect. That's a very big leap of logic, and the bar of sort of scientific rigor to make things like causal effects and real implications in the real world is much higher. So don't run linear regression, get a good result, and then say clearly these variables cause the effect or something like that, right? Because you can't make that statement most of the time, and frankly, even with these techniques I'm going to talk about today, you still can't make that a lot of the time. So you have to be very, very careful about how you sort of qualify the results that you get out of studies, at least using the techniques that we typically use in this course. So there are, however, huge reasons why we might want to really get at the truth in the world, right? Even in a context that's not, obviously with things like medicine or biology, those are all these fields are all of most scientific fields, most natural sciences at least, are really about finding truth in the world. In data science, though, beyond the obvious things like, okay, well, maybe we also want to analyze things like the effects of drugs and stuff like that. There have been a number of applications that have come up that people have really cared about that relate to things about testing effects in the real world. So a very common one, and there are really companies that probably at this point almost billion-dollar companies that base their entire business on this first thing. The idea is you have two websites. You want to get more clicks. Which website should you do, right? So the way you typically do this is you sort of offer some tests to people. You give one person, some people design A, some people design B, and see how they interact with these websites, and then you make a decision. In linear regression, you might want to say, okay, I have some error metric, but I also want to know, kind of at a true fundamental level, does some variable impact the output, the response we get? So, for power, does being a weekday or not actually matter? Does that really affect how much consumption people had? We sort of saw visually that we thought maybe it did, but how do we quantify that? And so really in both settings, the important thing here is these are really statements about the real world. This is saying, this design, people really will click on it more than the other design, or, being a weekday or not really does impact how much power people consume. And so we want to go beyond just sort of the notion of maybe just making predictions. I could predict for design A and design B how likely they are to cause clicks, but is that really sufficient here? And if not, then what do we really do? So asking this question is going to take us on a big detour because this is really, I should say, one of the central questions of statistics as a field. And I'm not going to do justice to it by any means at all. This is sort of basic stuff on some level. But I want to give some at least formulas or intuition that you might be able to apply, such that when you analyze your data for your project from real world systems, you can at least try to make an effort to maybe throw in a few statistical significance tests to see whether what you're doing really does in fact have any real correspondence to the reality. Okay, So let me start by jumping in some background with sample statistics and the central limit theorem. Hopefully this is things you have seen before in like a basic stats course, but if not, again, we will have some notes here, but this is going to be pretty fast. Okay, so one of the central kind of tenets of statistics is that you typically don't work with your entire set of data. So we typically refer to sort of the set of all things we might care about as the population, right? So there's, let's think about the population of all humanity. We can't test something on all humans, right? That would be hard. We can test on a small sample of them, okay? And on that sample, and on the population, these are things, I mean, because our people are like random variables drawn from this true distribution. The population has things like a mean, which is just the expected value of some random variable in that population. And it can also have things like variance, which is the variance of the real variance of this quantity as defined as by the real variance of this random variable. But we can't access those, right? What we have access to is a sample. Some small sort of number of samples that depend on this. And really this is actually the exact same thing we worked with before. We're just treating it in a more sort of, we're emphasizing the fact that it's a sample of data from the huge population more now. And so in particular, I'm going to define two things that people often do with two terms people often use with samples. I'm going to define the sample mean, which I'm going to call x bar. And that's just going to be 1 over m times the sum. So just the mean of our samples. We'll assume they're all real valued for now. This will apply to vector valued stuff too, but we'll assume it's all real valued for now. And I'm also going to define the sample variance, which not being sigma squared, I'm going to call it s squared. And this is equal to 1 over m minus 1 of the sum from I equals 1 to m of xi minus x bar squared. I'll talk about in a second why we use that 1 over m minus 1 rather. But it looks a lot like sort of our maximum likelihood estimate for variance for say a Gaussian distribution, except we have this weird m minus 1 term here instead of m. Okay, so now there are a few things that are sort of nice about this, which you might imagine. Let's look at the following two quantities. Let's look at the expected value of our sample mean and the variance of our sample mean. Okay? So these are just, I'm not going to write this down because this is just sort of math here. Maybe I'll write down the final things. But one sort of nice property is that our sample mean, the expectation of our sample mean, is also equal to the population mean. Right? That's sort of obvious. I mean, when you think about it, right? And it comes out just by the math here. If you just take this, the expectation of each sample is the same as the expectation, the mean. So you're just averaging, a bunch of, you're just summing together a bunch of means. And so of course the expected value of this thing is in fact the true mean. That's good. The expected value of a single sample is the true mean. So it's also good that the expected value of a sample average is the true mean. Maybe what's a little more interesting, and you can sort of follow maybe I'll write it here. So what's a little more interesting is to think about the variance of the sample mean. So this is a little more interesting now. So this equals the variance of 1 over m of the sum from I equals 1 to m xi. Though we didn't really emphasize it here, the variance is a quantity where if you multiply the inner term of a variance by some constant, that multiplies the whole thing by the squared term. So this will equal 1 over m squared of the variance of this thing. Sum I equals 1 to m xi. This thing here would be m times the variance of each xi. So this whole thing equals sigma squared over m. Okay? And so what's important here is that this is decreasing the bigger our sample is. So m is the size of our sample. It's the number of samples we select. And as you would hope, as you get a bigger sample, the variance of our mean estimate, in other words, the variance of not a single point, but the variance of our sample mean is decreasing. Okay, so it gets, in other words, our sample mean gets sort of closer and closer, and we expect, to the true mean. Now, we don't know this, right? We don't know this. So we oftentimes, what we will do is we will approximate this with our sample mean, sample variance. And we will sort of use this as our sample as our estimate of the variance of our sample. And this term here, rather the square root of this term, it's called the standard error. Okay. All right. So now it turns out that we actually have even more than this. So not only, and this is a really sort of amazing property, but not only is this sample mean, have expected value equal to the true mean and variance that sort of scales with 1 over m, but it also turns out that this sample mean tends toward a Gaussian distribution. So the sample mean itself tends toward a Gaussian distributed variable with exactly this mean and variance. So with the mean mu and the variance like that, right? And you can also write this as sort of saying that you can write this either as a sample mean having this variance, or you can write it as a scaled version of it going to a standard normal distribution. So if I subtract off the mean and divide by the variance, or the standard deviation, that will go to a standard normal distribution. This is called the central limit theorem. And it's really kind of an amazing fact, right? Because it says that no matter what the distribution of my actual sample, so each x could be binary. It could have nothing to do with having a normal distribution. Despite that, the sample mean itself, that sort of quantity, tends toward a normal distribution, which is really kind of it's sort of an amazing effect. It's why everyone justifies using Gaussians even when they're not appropriate, because it doesn't, of course, always apply in every scenario, but people often justify using Gaussians because of the central limit theorem. Now, there's one little caveat here. In practice, because of two things. First of all, this only holds really in the limit of lots of really big M that it approaches a Gaussian. So if our sample size is small, and if we're using our sample variance S instead of our S squared, instead of our true variance sigma squared, we actually can't use a Gaussian for sort of technical reasons. We actually want to use a different distribution, which is called a student t distribution. And so essentially, all this is saying is that instead of using this formula here, or really this one, saying that the scaled version of our variable goes to a standard normal distribution, we actually say that the scaled version of our variable, where we scale it by the sample variance, or the sample standard deviation, goes to a t distribution with what are called t degrees of freedom. You don't have to worry about these details here. Just know this is why we talk about t-tests and things like this, is about this distribution here called a student t-distribution, which essentially just looks like a Gaussian distribution with a little bit heavier tails. That's really all it is. And as actually the degrees of freedom goes to be infinite, this actually approaches the Gaussian distribution. Okay, so one more thing, which I'm not going to derive, but in case people are interested, why is there this weird m-1 term in the sample variance? We already just did, we showed, for example, that the maximum likelihood of estimate of variance would just be 1 over m times this thing. That's what we showed last lecture, I think, for a Gaussian distribution. The reason why there's an m-1 there is to make the sample variance be what's called an unbiased estimate of the population variance. In other words, and I won't prove this, but if I take the expected value of S squared, this actually equals sigma squared when I have this weird 1 over m minus 1 term there. Did I write something wrong there? Yeah. So if we don't do this, then actually you're off by a little bit. You're off by a factor of m over m minus 1. You tend, or m minus 1 over m. You tend to underestimate your variance a little bit. And for those that care, here's the formula. It involves a really weird. I mean, I actually don't. I honestly had to look this up to remember how to do this. It's not something I remember. You have to sort of do this weird thing where you take the expected value of the sample variance, you split it up by introducing the fractional mean, you square that thing and separate out terms here. One of these terms cancel with one of these terms, so you get this times m of that. And so there, the expectation of that thing actually equals 1 minus m of this thing. So to get that thing equal, you have to divide by m minus 1. It's not at all intuitive. It just actually is what sort of makes it. I mean, well, it isn't to me at least. Maybe someone else has a good intuition here. It's what you need to make this thing here hold. That's why we have m minus 1 term there. Okay, so that's sort of this is again kind of very basic statistics, the kind of thing you sort of learn in like a practical statistics course where you want to sort of analyze data and test, look at sample means, look at sample populations, stuff like this. All right, so let's then move on to what we do with these kind of things. What we do with these quantities in practice, which is, and one of the things we tend to do is basic hypothesis testing. So the idea here is of all hypothesis testing, as long as, at least as far as we're concerned, is that we want to determine, we want to sort of observe some data and determine if this data gives evidence that some effect really occurs in the world. Okay, so say I give a group of people a drug, and I want to know, does this drug actually help to cure this disease? Not just, can I use machine learning to predict whether this drug gives people, cures a disease, but does it really just giving this drug? That's just a question, yes or no. Will it help cure this disease? Right? And really, what this is about, because we can't, give everyone in the world, or even everyone that has the disease, the drug. What this is really about is this is about evaluating whether what we saw on a sample, right, the effects that we saw on some sample, can credibly let us conclude something about the larger population. Right? So we can, you can say for sure on my sample that I had 100 people that had this disease and I gave the drug to them, and 50 of them got better. You probably, we'll talk about a control group in a second. This is actually maybe a bad example. But the point here that I'm trying to make is that for the sample, you can say exactly what happened. You can just say what happened. And really, most machine learning, to be honest, is just about a very, very big sample that we use, right? We just sort of collect a big sample, and then we say how well it works on some other sample, which is trying to be an estimate for the whole population. But it's sort of very simple heuristics for that. What we're trying to do here is sort of say, okay, I'm just really thinking about this as a small subset of my entire data here. I want to know, can I say something kind of scientifically rigorous about what this says, this sort of sample effect says about the population as a whole? Now, I have to say that there are a lot of caveats about the precise meaning of these terms, about the nature of an effect really occurring, or what evidence is, or whether things are true about all the data. And it gets almost absurd, frankly, to the point where I think there's a lot of very relevant debate about whether this kind of hypothesis testing is useful at all. So people will, for example, argue that this kind of hypothesis testing just doesn't, causes more harm than it actually helps because it gives people the wrong impression. We'll talk about some of those misconceptions in a second. Or people saying that you really need like Bayesian methods for hypothesis testing because people just can't understand things like p-values and stuff like that. People just don't really understand what they mean. So that's all. I think that's all true, and actually I have very little to say about that because, as I said, most of what I do actually doesn't really fall in the realm here of real sort of truth in the world. But I think that these techniques, whether you end up using them or advocating for them or not, are incredibly important, and you want to know what they are, so at least you know, if you're going to critique them, what you're critiquing, if anything else, right? So it's very good to know sort of classical kind of frequentist hypothesis testing methods in order to sort of figure out what people are doing when they talk about p-values and kind of what that really means. So with that, we're just going to jump right into kind of basic hypothesis testing. Any questions so far? Been talking for a while. All right. So here is sort of the basic idea of all this kind of hypothesis testing. The first thing we're going to do is we're going to posit some null hypothesis H0. Okay? And the assumption is that this thing is what's true. The default assumption always is that H0 is actually what's true. And then we have some alternative hypothesis, H1, which is usually just something along the lines of saying H0 is not true, right? So it's usually, we'll talk about sort of things like one-sided tests in a second, but usually it's just saying, hypothesis says maybe there's zero effect to this thing, and the null hypothesis, or the H1, the alternative hypothesis says, no, there is some effect of this treatment here. Now, if we're given some data, X, that we're using to test our hypothesis, say for example, if I'm given a series of numbers, the simplest one that we're going to use in a second, maybe I'll just make it concrete now, is we're going to ask, is the mean of these numbers 0 or not? Right? Is their mean 0 or is their mean not equal to 0? So given this data, we want to accept or reject the null hypothesis. So, or maybe I should get this example last time, right? Flipping a coin, right? I want to ask, is this coin biased or not? So, I'm going to flip a coin a bunch of times. My null hypothesis is this coin is unbiased. It is a 50-50 coin. As I say, most coins I see in the world are in fact unbiased, as far as I can tell. So the null hypothesis would be that this coin is unbiased. The alternative hypothesis would be this coin is biased. It has non-0.5 mean. And if we sort of lay out what can happen here, there's a couple of things that can happen, right? We're going to use our data to somehow accept or reject the null hypothesis. We're going to say, okay, I accept it. I accept that this coin is unbiased, or I reject it and I think the coin's biased. If we accept it and it's true, we're just correct. Things are good. If we reject it and it is in fact false, then we're also good. We're okay. But there's two very different types of sort of errors we can make here. So if H0 is in fact true, so if the coin is in fact unbiased, but we go ahead and reject that, we say, no, I think it's biased, we've made what's called a type 1 error, or a false positive. Right? We talked about this a little bit, the kinds of classification, but the same kind of terms apply to hypothesis testing. So this is called a type 1 error, or a false positive. The other one, the case where we accept the null hypothesis even though it's not true, it's called a type 2 error, or a false negative. And though this is, of course, completely arbitrary to a certain degree, the general consensus is that this is the worst kind of error here, right? Because when you say, you sort of believe for some reason the null hypothesis to be true, or if you're going to reject it, you want really strong evidence that it's true, right? So this is saying that, I have really strong evidence, but I'm still wrong about it. Whereas this one is saying, maybe I just don't have enough evidence yet, or something like that, or this test wasn't powerful enough to really figure it out. But I'm kind of going to play it safe and just accept it, even though maybe it's not true. I'm just going to kind of play it safe. So there's a very sort of significance to these different regions here, and the two that you should sort of be aware of is the first one here, which is the probability that I reject the null hypothesis given that the alternative is true is called the power of the test. So the bigger the power of the test is, the more. So you can think of a larger sample size, for example, would give you a more powerful test, because I would be sort of more and more confident in my estimate that I would form from my sample size, that I'd have sort of more ability to reject the null hypothesis. Whereas a test where I have only one sample would not be a very powerful test because I wouldn't really be able to reject if I flip a coin once and it lands heads, I really should not complete anything about it being biased or unbiased, so that really probably would have no power, a test with one coin flip. This here, and we'll talk about this one a lot later, is that this is the probability that we reject H0 given that it's true. So this is our bad mistake we've made here. We've said that the coin is unbiased, is biased, even though it really is unbiased, and that probability is called the significance of the test. So we want the significance to be low. We want it, or the significance level of the test. We want it to be low. We want to say we believe this to be true at the significance level of 0.1 or something like this, or the p-value of 0.1, right? So this is going to be, we want to make this as low as possible while also making this thing kind of high here. Okay, so that's going to be that's going to be our goal for designing hypothesis tests. Okay, so let's see how this actually works. The basic approach to hypothesis testing, this is kind of the current way what's usually done these days, and again in the kind of this frequentist mold, is you compute what's called a p-value for your data. Okay, and the direction here is really important. All right, so the p-value is the probability, approximately, the probability of your data given that the null hypothesis is true. People say that p-values aren't probabilities. They are. They're just this probability, not a different probability. Okay, so the p-values is the probability of observing a certain amount of the data that you observed, given that the null hypothesis is true. Okay, so if I flip one coin and it's heads, and the coin is unbiased, there's a pretty reasonable probability of that happening, right? If I flip a coin 100 times and it's heads, then the probability of that happening under the null hypothesis is pretty small. So you'd have a small p-value. What you typically want for hypothesis testing is you want to have a small p-value, because this means that I can reject that. This means that the probability of the data being generated by the null hypothesis is pretty small. Therefore, I'm going to typically accept the alternative hypothesis. So the idea is, you reject the null hypothesis if the p-value is below some threshold, where we pick the threshold by pulling it out of thin air, or by looking up, what people have done in the past, which is always 0.05. But really, reporting the p-value itself is the important thing. So you want to know, like, what's the significance level at which I can reject the null hypothesis, basically. Now, here's sort of the important part of all of this, which is where everyone gets it. Every article you read in the news will always get this wrong. The p-value is not the probability that. Oh, sorry. This should be H1 is true. Let me fix that right now. Or really, I should say this. Okay, no. Right. No, okay, this is correct. So the p-value is the probability of data given that this is true. It is not the probability that this is true given the data. And that's really important, right? So when people say, this drug is effective with probability, 1 minus the p-value, that is absolutely incorrect, right? That would be saying that's the probability of H1, i.e., H0 being true is equivalent to H1 being false. That would be saying the probability of the alternative hypothesis is 1 minus the p-value, right? So I'll just write this here. So the probability that H1 is true, in other words, our coin is biased, our effect is significant, whatever, given the data, is not equal to 1 minus the p-value. Okay, so people, and people say this all the time, saying like this drug's effective with 99% probability this drug's effective, right? Because the p-value is 0.01, and that's completely false. In order to transition here, of course, right, you would need some notion of a prior probability. So some sort of Bayesian estimate maybe of how likely I think both the null hypothesis and the alternative hypothesis actually are. With hypothesis testing, you cannot do that because we're not ascribing any a priori likelihood to either the null hypothesis or the alternative hypothesis. We are just computing this value here, which is the probability of the data, given that it is true. And we have this kind of fuzzy notion of rejecting it or accepting it if that thing is low enough. Okay, so it's a very, and this is, by the way, why people kind of complain about p-values to a certain extent, is because they are not very interpretable. And it's very tempting to say that I believe, because the p-value is really low, this implies that the hypothesis, the alternative hypothesis, is true with high probability. But this is saying nothing about the probability of different hypotheses. It's just saying about the probability of the data given a hypothesis. Okay, so know that it goes that way, not the other way. Any questions there? Because that I kind of rambled on that point for a while, but it's a very important point, and this is also why people, really complain about p-values much of the time. Yeah. Correct. Yeah, that's absolutely correct. So there's no notion of the probability of H0, the prior probability, nor the prior probability of H1. If you want to have those things, you can compute Bayesian hypothesis tests then that actually tell you, under those assumptions, what the probability of your alternative hypothesis is. But you cannot, from hypothesis testing, determine the probability of a hypothesis being true or false, given some data. That is just, that's not something that's not a quantity that it makes available. P of data. No, there's no problem. There's no notion of this either, because under what model of probability, right? Under the, given the null hypothesis, there's that. But otherwise, you'd have to. Otherwise, P of data would be equal to the sum over the hypotheses of P of data given the hypothesis and then probably the hypothesis. But we can't do that, right? We don't have this term here, so we can't do it. So this term doesn't exist either. Okay, so I want to just do a quick poll here of the title gives it away a little bit, the answer. But these are also things that are very common. And actually, more than the answer here, I'm going to ask people why they think this is true or not. So the idea here is that we're going to run the following test. We're going to test 100 patients to see if a drug has a statistically significant effect. And if so, we're going to stop and say, here's our p-value. If not, we're going to collect 100 more patients. We're not going to throw out the first 100. We're just going to collect 100 more. Maybe our significance is not low enough yet. It's like p-value is like 0.007. So we want to have clearly our test is going to be more powerful. So we're going to add a few more people to our test and compute the p-value again with the entire sample. And then we publish that p-value. In fact, at that point we're going to stop. Whether it's significant or not, we're just going to stop at that point. So is this a valid experimental design? So that's what people said. All right, so most people said no, it's not valid. Some people with some amount of support for the other two options. So who wants to argue whether or not it's valid? Who thinks? Well, yeah. So someone will argue that it is valid. I'll argue afterwards that it is valid, just for the sake of it. Who wants to argue that it isn't valid? Someone has to answer. We just stay here too long. There were how many people? 150 or so that answered that it's not valid. Someone chime in. Does anyone argue that it is valid? That would be even better, actually. All right, I'm going to call on someone randomly if no one volunteers. So we'll say All right, so let's see, so in the yellow shirt there. Yes. Yeah, you wear a very colorful shirt, so it makes it easy to indicate.
I'm going for no.
Okay, you think it's no? How come?
Because we're basing our conclusion on a variable sample size. So in the first sample size, the number of computations doesn't satisfy, and we're just collecting a few more, then if it does satisfy.
Oh no, but I'm using all of them. I'm using all 200 to compute that. Yeah, no, definitely wouldn't be valid to just like keep trying 100 more, a different 100. Nah, we'll try this 100. Yeah, no, what I'm saying is, okay, you know, I tried the first time. I didn't really maybe just didn't have a big enough sample size the first time to get a significant, you know, a powerful enough test. I'm gonna sort of select the next, you know, a little bit more, and increase my sample size. Does that change anyone's opinion? All right, who else has a colorful? Yes. Yeah, I think it's getting at the right intuition. Yeah, I think you're getting there. So this is not valid. You can't do this. And this is actually very, very common in practice, right? Because tests are expensive to run. People really want to know. They got to hit that, you know, magical. We'll look at the at the end. There's this magical p-value of 0.5 that, you know, makes your paper published versus not being published. That's sadly actually true empirically. So there's this magic value of 0.5. And so people aren't, you know, studies are expensive. People are not going to recruit, you know, a sample size of 10,000 if they think they need a smaller size at first. They're going to do the small size first. If it isn't good enough, they're going to just get some more and add to it, right? And you can't do this. And the reason is that essentially, I mean, so it's easier to see if you sort of think about like tracking like a running sample of all your, you know, people one at a time, right? So if I just have like a running sample of the p-value when I add one more person and one more person and one more person, right? If I do that, then there's always, I mean, it's not quite as bad as just selecting another 100, another 100, another 100. But there's always this chance that you stop at a point where sort of you've gotten the most lucky in like recent history. And so you stop at the point where you're sort of the most lucky in recent history. I got a few good samples. And so, you know, in the trace of my p-value, it does something like this. You know, maybe it starts off high because you needed some sample, and then it does this, and then, you know, maybe it dips down and then comes back up here and then dips down again. And you're basically looking at these places where it like you're sort of determining where you stop based upon the exact sort of behavior of this p-value going along. And so it isn't really anymore the probability of your data, given that it's true. What it's now, it's the probability of some weird sort of set of correlated, you know, tests where it's the probability of my data up to the point where that thing is less than 0.05, and then I stop. And so this is a very weird process that is no longer the same as the process you have if you actually, you know, collect a fixed sample and then stop. It introduces an additional variable sort of into your process of data generation in some sense, and so you can't claim these same things. This is very, very common, right? Because as I said, people are very reluctant to hire large groups. You know, we want to make a powerful test, but we want to make, you know, maximize the power of the test versus the money we spend on the tests. And so we want to just keep adding a little bit more until we get the right amount of power for the test. Now, I should say there are actually ways of modifying your test to let you peak as much as you want, but it's a different test you have to run then. It's not the standard ones that you typically run. So there's a whole sort of literature on what's called p-value hacking, which is basically trying to, you know, mess with the data in clever ways to get your p-value as low as possible, which is not allowed. Yeah?
So would it work if you just throw away the initial 100 and collect?
If you throw away the initial 100 and collect 200 more, it's better. I actually think there's still a problem with that in that you are still basing your data upon conditioning on the fact that I didn't get the right value the first time. So it's still a weird data generation process that's not a random sample. But I believe that procedure is better. Because you don't have this problem of like, you know, I just wait till like I get the right exact 100 and then I stop there. It is better, but it is not still a valid thing. You can modify it though to make both those procedures valid. You can peak it so that you can peak as much as you want. You have to just basically inflate your p-values a little bit. Yeah, there's a question right there.
In this situation, is there an underlying fact that the initial sample was not a true representation of the population?
Okay, sorry, I should repeat the question. So the question was, is this the case here that the original population was not a representative sample of the overall population? And no, not necessarily. So there's a lot of reasons why you have a low p-value. We'll see in a second, sort of computing these, though we'll give the formula, but it's not always obvious, kind of the intuition here. So one of the big reasons why tests are not significant as to a certain p-value level is we just don't have enough samples. So the p-value was, think about the coin flip, right? If you flip a coin once and it ends up heads, that's a perfectly valid, sample from that population. I mean, it has to either be heads or tails, right? Yet at the same time, you will not have a low p-value because your sample size is just not big enough. So the p-value will be affected by the sample size, as we'll see in a second, actually. So it could be you just needed a bigger sample. Your effect could really be there. You just need a bigger sample to demonstrate your effect. And you picked wrong. And so really, statisticians are involved in the planning stages of experiments too, because you want to make sure that your test has sufficient power. In other words, if the effect really is there, you want to be able to catch it. There's one more, yeah.
Back to the previous one. Isn't the reason why we can reject the null hypothesis is because we think T of H0 given theta is also low because the p-value is low?
You might be implying that, but that's actually not at all what's happening. So the question was, aren't we rejecting it because we think this is small? But no, that's not the case here. We don't. Our rejection of the null hypothesis has nothing to do with the probability of the null hypothesis itself. It has to do with the probability of the data given the null hypothesis. And so, and it's sort of weird, right? Because why would that matter in some sense? We've already seen like the flu thing with the false positives being really high, right? Like the number of false positives being really high. So that's definitely true. If we believe that this is, if our intuitive prior on this is really big compared to our intuitive prior on the other one, we would need a really, really small p-value to really reject it, to really believe that the probability of the hypothesis is lower. And this is why people sort of advocate for Bayesian hypothesis testing, is because this is not based upon any notion of the probability of this being true or not, because we don't have that. We just have this weird notion of if the probability of the data given the hypothesis is low enough, then we reject that, whatever that means. Okay, let's move on to the actual tests we run. Okay, so I'm going to give a few of these formulas here, but really what I'm going to show next slide is the picture of what's happening here, and the picture is actually more important than what's really going on here. Okay, so here's the sort of canonical example. So we're given some sample, x1 through xm, and I want to know, I would like to know, but I shouldn't phrase it that way. Our null hypothesis is that the mean is 0. For the means, this is the population mean is 0. And our alternative hypothesis is that the mean is not equal to 0. Okay, so by the central limit theorem, we know that our sample mean minus the true mean divided by the sample variance scaled by the square root of m. Does this formula make sense to everyone? Remember, so let me just actually emphasize that. So that's going to appear a lot, and there's a lot of terms there, so I want to emphasize what's happening there. I also have to get it on one line, so it's sort of condensed that that expression. So remember, our sample mean, the expected value of this is equal to mu. The variance of this thing is equal to the sigma squared over m, which we're going to approximate as our sample mean squared over m. So in order to scale this thing to be like a 0, 1, or a Gaussian random variable, say, we would first take x bar, subtract off the mean, and then divide by the square root of the variance. In other words, we divide by the square root of s squared over m, i.e. the standard error. And this thing, according to the central limit theorem, is distributed with the t distribution with m minus 1 degrees of freedom. Okay, so this is sort of what I'm saying here. And this is the fact that we're going to use a lot. Okay, so what we're going to do is we're going to compute this thing, the test statistic. Remember, our mean here that we're supposing is 0. So we're supposing it has, what we're trying to say is that the null hypothesis has 0. So I'm going to compute our test statistic under this assumption that it is in fact 0. And this we're calling t, and this is just this thing, 1 over the square root of s squared over m. All right, so t is that thing. And now we compute the probability that our p-value, which is the probability that under this distribution, the t student t distribution, we are either bigger or less than that thing in some direction. Okay, so this is just ends up being actually the cumulative distribution function of in fact our negative test statistic, or the negative absolute value of our test statistic. So that's a little bit convoluted there. Let me just show what we're doing graphically. All right, so here's what we're doing graphically. What we're doing here is we're computing the probability density of our test statistic that we observe given the null hypothesis. Okay? So this is a plot of the density of our test statistic. It's probably, it's not a probability anymore. It's probably the density because it's continuous. The density that given the null hypothesis. Okay? And what we're going to do is we're going to sort of look at what, basically what we're computing, our test statistic t there is the value that we actually would compute for that thing from the real data, right? So under the null hypothesis, we would expect our sample mean to have this distribution. We compute what the actual sample mean is. And then we look to see, what's basically the area above and below that sample mean. And that's the probability that something, that our observation or something more extreme would happen given the null hypothesis. All right, so all the p-value is basically what we are doing is we are finding a distribution of our test statistic or the sample mean given the null hypothesis. We are seeing where our actual experiments lie, and then we're computing the probability that or something more extreme happens. And that is our p-value, which just corresponds, in fact, to the area under here, where this one here basically is where we end up. Okay, and the actual math for that is this thing. It has to do with the cumulative distribution functions of the t distribution, but that's just sort of comes out of the central limit theorem. So that's sort of the details. The intuition here is this. Any questions on that? All right, so if you want to see this in code, there is, so basically, here's how we compute sort of manually the t statistic and the p-value. We would compute, so we have some random sample, x, and in fact it does have mean 0, so this better not give too low a p-value here. We compute s bar first, which is just the mean that we see in our sample. Then we compute the sample standard deviation, which is the sum of our things minus x bar squared divided by m minus 1. We compute the standard error, which is the square root of this divided by m, and we compute then our t statistic, which is the sample mean divided by the standard error. Okay, that basically is just taking this distribution here. Just to be clear, here what's happening here is that we're just scaling this thing here. We're just taking this rather than being x bar, we're taking a scaled version of x bar here, so that we can use a standard t distribution instead of like a scaled t distribution. Then we just compute the t actually, I don't know what this is what I actually care about here. This is a t statistic. This thing here is basically our, I think this is like if you want a certain level of alpha, but we're not going to worry about that. So our p-value then becomes 2 times, sorry, this is the actual, like, this is like how you say in SciPy stats, like what the distribution is. I think this should be just TD here. I think I might have corrected that as a somewhere in the code without actually running it. So this is our like t distribution, our standard distribution that we have in SciPy stats. And we compute the CDF for that distribution, evaluate it at the negative absolute value of t. That is saying, and we multiply by 2. The negative, the CDF up to here, the first one would just be this area here. And then we multiply by 2 because I want both tails. I want this tail and that tail. So that's how I compute my p-value in SciPy. By the way, this would be exactly the same. SciPy has a built-in, or SciPy Stats has a built-in t-test. T-test one sample. You just run this thing here. I should even forget what that second term is for. It's 0 here. You can make it if the mean is 0. That's right. It will give you the same values here for the t-statistic and the p-value there. All right. So this is just sort of the manual way of doing what this function here does. Okay, any questions? So again, our null, remember, it's important because our null hypothesis was that it's 0. Our alternative was that it's not 0. So we're fine actually being on either side, right? We can be either really small or really big. We still reject the null hypothesis. That actually is, yes, question.
But is the probability of X bar given the null hypothesis, like you have to have a prior probability of the null hypothesis? Where is that?
No, there's no notion. So you mean where is P of X bar given H0 here? Like where's this given part here? So the given H0 part here says that if H0 is true and you have 0 mean, then X bar will be distributed according to a t distribution with this degrees of freedom. So the H0 here is implicit in the fact that we're evaluating the CDF of the t distribution. Yeah, but there's no H0 probability of H0 here or anything like that. Okay, now admittedly, it seems a little odd to if I'm trying to estimate something as a good effect, it seems odd to sort of consider both tails there. You think you would just say, well, I don't really care if like the drug is really, really harmful. I shouldn't go ahead and say like conclude this is statistically significant because it's really harmful. Or at the very least, I want to know which direction it's harmful or helpful in. So maybe more common than this is actually a one-sided test, where the null hypothesis actually is that, say, the mean is greater than 0. It could be anything as long as it's greater than 0. And the test statistic, the alternative hypothesis says mu is less than 0. You would actually run the exact same procedure there. You would just not double. The p-value would just be not double this. It would just be equal to the f of the t-statistic. And that's just going to be the area on this side. So if it's down here and this is small, you can sort of, say, okay, that looks like it's a good reason to reject, maybe, again, without ascribing any probability to how likely we should be able to reject it or things like this, just saying, yeah, we're going to reject it because the probability what we observe is small given that. But here we just have one side. So we don't include this as also being a good area. If our test statistic is over here, we ignore things. Or rather, we don't reject the null hypothesis. Okay, one last thing here. I hope this is the last thing because this is getting now kind of this notation gets pretty ugly. So remember, X, we believe, X bar, has mean mu and covariance sigma, S squared, variance S squared over M. So if we want to know, and we believe this thing, not only that, but it also has distribution according of this. It has the distribution of this t distribution. So with M degrees of freedom. So more than that, we can also use the same procedure to compute what are called error bounds or confidence intervals for the mean. Now, very important here. This is not, so this is actually an important thing when you report your results to, incidentally. When you take some average of some population and you report what your sample mean was, what this lets you say in some sense is it lets you say that this will imply that the true mean is equal to the sample mean plus or minus some error term. Right? So what I can say is I can here's my measurement of the sample mean I got. I can say, look, the true mean I think lies with somewhere in that range with 95% probability. Okay? The way I get that, this error bar here, is just the following. So I take the inverse CDF actually of my distribution, which is the t distribution here, at some significance level. So alpha here would be like 0.5 or something like this, 0.05. And then I scale it by the variance. That's how I get my error bars here. Don't worry about that. This is more of like a formulaic thing. If you want to estimate your mean, you report the mean plus or minus. You report basically the mean here, x bar plus or minus the standard error, so the square root of s squared over m times this weird thing that gives you some scaling of that. Okay, so what is this actually doing? Now, importantly, what this is saying is this term here is not an estimate of the standard deviation of each sample. It is an estimate of some error bars for the mean itself. So this thing will of course get smaller the more samples I add, whereas the actual standard deviation of the actual population will not change over time, no matter how many samples I have, right? This thing will get smaller and smaller. So this is not saying how big the variance is. This is saying how close we think we are to the true mean. Kind of a subtle point, but note when people say to confidence intervals, they usually mean a confidence interval of the mean, the estimate of the mean, not an estimate of the actual sort of population standard deviation or something like that. That's a subtle point, but if you've got that, great. If not, honestly, don't worry too much about that. And here's the code to do it if you want to. Okay. So I just want to say a couple last things. We only have about 15 minutes left. I want to say a couple last things about this and experimental design. So up until now, we've assumed that the null hypothesis has some known mean, right? So we assume that the null hypothesis is that this drug has no effect, or that we know that the null hypothesis is that the coin is unbiased, something like that. But in a lot of situations, we don't really know what the mean is that we want to compare to, right? So we have 2 web pages, and they each get some clicks, and so what's our null hypothesis there, right? Sort of unclear, right? Yeah. So essentially the point here being is that if we want to add some feature on our site that says we want to test if this feature makes people stay longer on our site, we need to both compare sort of what the current site does with what this new site does. And this leads to these notions of A/B testing or control group testing, right? So I sort of actually haven't mentioned that much or mentioned it implicitly so far. But the reality is, typically you don't just have one group you're testing. I don't just collect some data and then evaluate a hypothesis on that. What I often do is I will collect 2 groups of data and then run a hypothesis test on those 2 things. And when I have 2 groups, so I'll have a control group, i.e. one that I showed the old website to, and a treatment group, it's called, one that I showed the new website to. And my hypothesis is set up in this sort of 2-sample setting is that my null hypothesis is that the 2 means are equal. In other words, this doesn't change anything about the website. And that or maybe that the first one is better than the old one, and my alternative hypothesis is that they are not equal, or that the new website redesign actually improves upon the old one. So this is sort of how we go from a single sample test to 2 sample tests, to test where you're collecting 1 sample of a control group and 1 sample from a treatment group. Now, okay, so we do this. We collect 1 sample of some size from website 1 or set of patients 1, where we just give them either the old website or we give them placebos if it's a control group for a medical study. And then in our treatment group, we show people the new website or we give them the actual drug. And now you compute what's called, well, there's a bunch of things you can do, but one of the more common ones is called independent t-test or Welch's t-test. The idea is you collect 2 number of samples, one from your, from both populations, from your control group and treatment group. You compute the sample means for each of these things, you compute the sample variance for each of these things, and you compute a test statistic, which is this very intuitive form here of the difference between the 2 means divided by this sort of weird sort of geometric average of their variances. And then you evaluate a t-distribution with the degrees of freedom given by this thing here, obviously. So as you can kind of guess here, the point is actually not for me to explain that or for you to sort of remember that, because it's starting to seem a little bit ad hoc or kind of crazy here. There actually is a good reason why you choose all those things. Like if you can show that all these things will be distributed approximately. This will have an approximate t-distribution with this degrees of freedom, but it gets a little bit hard to see why that actually is. And so you probably don't need to remember these. If you ever need to use them, you can probably look them up. If I say, okay, I have a 2 sample t-test that I want to run, how do I find that? Well, you just go look up, and you'll see in either in Scikit Stats package that you either just run probably a function for that for Welch's t-test, or you can get the formula there. But the basic idea really is the same here, and so I want to emphasize the idea more than the actual specific tests you run, because those tests they're very ad hoc and they have to do with essentially convergence in distribution to these different distributions according to the central limit theorem. Basic idea in all cases is the same. What we're trying to do is we're trying to find the distribution of our test statistic under the null hypothesis. So that's this plot here. This is our distribution of our test statistic, or in this case just x bar, but our test statistic is just a scaled version of that. We find the distribution of that thing under our null hypothesis, and then we evaluate the probability of that test statistic or something more extreme, and that is our p-value. Right? And this is how, and then you determine whether you reject or accept the null hypothesis based upon the probability of your test statistic or something worse happening given the distribution that it should have. Okay? So really it's just about computing what distribution of your test statistic should be. And all those different tests that you see, and there's hundreds of them, all they are just about different distributions that we expect to see based upon slightly different setups for your problem. So if you have 2 samples and you have certain assumptions here, you expect to see this distribution. If you have 1 sample, you would expect to see, let's just die, oh, okay. You would expect to see this distribution here, okay? So that's the high level. It's really just about finding the distribution that you should have for your test statistic and seeing what's the probability of that happening. One more thing, because it is useful actually, this one people actually even here might want to use for a final product or something like this. This whole procedure, I won't go into the derivation here, but this whole procedure actually also works to determine the significance of coefficients in linear regression. You can actually use the same type of procedure. And they essentially work like this. So if I have a linear regression task, I can compute a estimate of the sample variance under that regression model. And that takes this form here. Interestingly enough, it's actually to make it an unbiased estimate now, you have to divide by not just m minus 1, but actually m minus the number of things you can tune, which are the number of your parameters, or it's m minus n. It's for normal linear regression, no regularization or anything like that, just normal linear regression. So I can compute basically my errors that I get with my learned theta. I can compute the errors of it. That gives me a sample variance estimate for my linear regression model. I'm not really deriving this. I'm just sort of telling you this, and you can look it up. I'll discuss it a little bit more in the notes, but really I'm just sort of telling you as a procedure to do. Next, I can also actually compute a sample covariance of the coefficients themselves. And that's like my standard error that I had before, but now it's actually a sample covariance. Because I don't just have one thing I'm estimating. I'm not just estimating one thing, the mean. I'm estimating now actually a whole vector of things. So I'm going to have a covariance instead of a variance. So this is an estimate for my sample covariance. And now I can evaluate a null hypothesis, namely that this coefficient should be 0. So my null hypothesis is that this feature here does not matter. And my alternative is that it does matter. Using this quantity here, this thing divided by its square root of its covariance, which is actually just like I was doing before. It's actually possible to show this is exactly the same as if you have only a single feature, which is a 1, which is a constant value. Actually, this reduces to the exact same thing as before. But this is the general case. This is saying that I take my feature, divide by the square root of its variance, and that will also have a t-distribution with the number of degrees of freedom equal to, I think, m minus n. And I can actually evaluate the probability of that thing, and that will tell me if I can say with certain probability or with a certain p-value, what is the p-value for this particular coefficient being not equal to 0. So how likely does this data say? No, I'm saying it the wrong way again. Given the null hypothesis that this coefficient is equal to 0, how likely is it that when I run my regression, I will get the value that I actually observe? Okay, so this is kind of nice because it can give you one way of, and there's lots of ways you can do this, but it gives you one way of forming an estimate about what we think is a real effect in linear regression, as opposed to just some random effect of the data. So if I want to know, does the presence of a weekday or not really affect whether or not I or what my peak demand is, I could run the linear regression. I can just run linear regression as it is here, compute the statistic, and see, if it was 0, what would be the probability of observing exactly what I observed anyway. Okay, so you can do all the same kind of things, not just for sample means, but for more interesting kind of quantities you estimate from data. Okay, so and again, this is just sort of, I want to say this briefly. It's not being derived here, but this is sort of falls out from the exact same principles we had before. Okay, so the last thing I'll say, and this is our last slide, is that, and this is the thing we've kind of been harping on, which we keep coming back to, which is the fact that the basic problem here is that people want to interpret p-values as the probability of the null hypothesis, or they want, or equivalently, 1 minus the p-value as the probability that the drug is effective, right? Or the probability that your new website is good. And you can't do that. And this is a fundamental problem with p-values as they are presented here. And they are frequently interpreted as such, despite every attempt by the statistics community to hammer in the fact, and despite my attempts to hammer in the fact that this is not how they're interpreted. That's problem number 1. Problem number 2 with p-values, I think the title p-values considered harmful is the title of of some paper. I forget where that's from, but that's sort of a well-known phrase at this point. The second problem, though, is that people, because we sort of have come up with this sort of this magical value here. And for some other reason, we come up with this magical value of 95%. Means that something is significant if it's 95% of the time or more. Even though this isn't really a probability of the alternative hypothesis, people still say that for some reason we have this affinity for p-values less than 0.05. So people will say that when p-value is less than 0.05, that is statistically significant, and if it's greater than that, then it's not significant, or you need to run more experiments. So there's a paper a few years ago that looked at 3,500 published journal papers and plotted the p-values that they report in those journal papers. And what happened was there's a very apparent little bump of p-values right up to 0.05, which is really concerning. What this means is that either the reviewers of papers or the authors themselves, this would not happen by any real effect, right? This is not actual science telling us this. What this is saying is that in order to hit this 0.05, 0.05, people are doing this p-value hacking we talked about, and they're running their experiments just long enough until they hit that magical threshold. Or maybe alternatively, reviewers read papers and their paper says, p-value 0.55. They say, oh, that's not significant. But if it's 0.49, they say, yeah, 0.049, they say, yep, that's significant. So there's some sort of institutional bias to influence us to report in journals p-values that have no business being, and that we know are scientifically invalid. Right? We can't say that any given study is invalid here, but as a whole, you can say clearly there's something sort of been going horribly wrong here with reporting of science. And this is real science too. This is not, my machine learning algorithm got this accuracy, which I think we can have a little bit more forgiveness for, because that's not really a statement about the world. It's a statement about an algorithm or maybe even a data set. This is saying something really fundamental about that that is just sort of clearly wrong from the papers that we have. If you can sort of imagine, if instead of saying that we got 96% on a certain data set, we said that this classifier get 96% error period on this problem period, on images as a whole, we would never buy that as a community because we know it's not true. These are trying to say something about much simpler problems. They're trying to say something that's real, and there's clearly something sort of going on wrong here about these effects. So while you should use them, you should also be very careful about knowing that a p-value of 0.05 is nothing to chase after. Yeah.
So if you can't draw any conclusions from low p-value, how is hypothesis testing?
Well, the question was, if you can't draw any conclusions from a low p-value, why is it useful? I think it's a little bit unfair to say you can't draw any conclusions at all, right? Because it is saying, what it's saying, literally, is that if this thing were true, this data is really unlikely. Now, it's up to you to infer what you want from that, but it'd be reasonable to infer that this thing is probably not true then. H0 is probably not true if the data is super unlikely. When you're saying, unfortunately, 0.05 or 5% is not that low. If your p-value is 10 to the -6, that's pretty good evidence, right? I think actually for the Higgs boson, when they found it, they were really just about trying to get their p-value super low for their thing. They sort of already knew where it was. They just, when they announced it, they just meant they achieved some level, basically. If you get it low enough, you can be pretty confident, right? If it's 10 to the -6, you're pretty confident. We, for some reason, have this weird affinity for this number, 0.05, and that is very bad, because if you run 20 experiments, one of them is going to be significant at the p-value. They're all random. One of them is going to be significant at the p-value of a 0.05. So you definitely need to, I think as a sort of a, there have been many, I'm not in this, I don't do much hypothesis testing, but I think people that do have sort of unified around a call for greater rigor and more understandable and interpretable sort of metrics by which they evaluate these things.